Hello friends, last class I have discussed about the what is optical fiber and evolution of the optical fiber as well as the where we can use the optical fiber and elements of the other components of and as well as the other components of the optical fiber system. Normally, we know that through the optical fiber used to send the optical signal as rather than the electrical signal, right? So, what is the nature of the optical signal? What are the characteristics and behavior of the optical signal, right? So this I will discuss now. So optical signal, so this is optics and information, right? So this optics, it is a electromagnetic wave. So it consists of electric field as well as the magnetic field. Okay, so electromagnetic wave, that electromagnetic wave. So this electromagnetic wave, the range of the electromagnetic wave, this I have already discussed in the last class. It has the visible various range, the RF wavelength, microwave wavelength, near infrared, visible wavelength, X-ray, gamma ray, so on. Right. So the electromagnetic wave, so it has the particle nature, two different kinds of the nature, particle nature and the wave nature. Particle nature as well as the wave nature. So from the particle that it has the consist of the photon, the wave nature. Wave nature means it should have some wavelength. Okay, it should have some wavelength, lambda. Wave nature is when the light is, suppose there is a source, when the light is emitting from the source, so it's not like a straight line. It is providing the photon as well as the it has it is emitting like that. Wave nature. So wave nature means the lambda. Lambda means the peak to peak difference. If you define the lambda, how can you define the lambda? Lambda is the peak to peak difference of any wavelength, any wave signal, right? So normally in case of the optics, whatever optical signal we used to prefer for optical communication, this is the 400 to 700 nanometer wavelength. The optical signal which has wavelength from 400 to 700 nanometer, such kind of wavelength may be used for the visible light optical communication, and above 700 wavelength, above 700, those things above 700 to 1300, 1550 nanometer. These wavelengths are used for the near infrared or infrared, NIR or IR, near infrared or infrared signal, wavelength signal. So these are normally used for the long range communication. Long range communication. So characteristics of the optics means it has the optics, it has the electromagnetic wave, it has the particle nature as well as the wave nature. Wave nature means it should have some wavelength. So wavelength, the peak to peak difference of any wave signal. So it is emitting, emitting or transmitting like this way, like wave only. So 400 to 700 nanometer, that is used for the short range communication. Above 700, 700 to 1300 or 1550 nanometer, these are used for the near infrared and infrared wavelength. These are the nature of the electromagnetic. So based on the electromagnetic wave or based on the electric field and magnetic field, some nature of the wavelength also change when it propagates through the optical fiber. Now come to the characteristics of the optical signal. So behavior of the optical signal. So when you see, it follows the law of reflection. Already, so we have already studied this thing on the class 11, 12. So there is an interface, right? So when the light fall on the interface, either it will be refracted or it will be reflected based on the media and the where. So what is this media? Suppose this is medium 1, this is medium 2. Based on the media, the light will be reflected, transmitted, and then it will be refracted. When it penetrates through the other media, so that means it is refracted. Okay, refracted. And when it is hits the interface and it is come back, that means it is called the reflected. It is called the reflected, right? So normally light has a behavior which can be reflected, okay, which can be reflected when it hits on the interface. So normally any interface. So if the visible light is there, if light falls on the interface, it will be reflected back, and if you have the eye, so it can be captured by your eye. Okay, so refracted and the reflected. So here the type of reflection. When you think about the reflection, suppose it is hits the interface and it is come back. So in types of the reflection, then there is a specular reflection and the diffusion reflection. The specular diffusion is what it is. So it is the interface. So light hits the interface. So light hits the interface parallelly. Suppose parallelly. So these two lines are parallel to different signal. So it will be reflected like that way. So this will be also parallel. Okay, this will be also parallel. That is reflected. So I have not drawn properly. This will be parallel. But in case of the diffusion, what will happen? Suppose light is incident here and here. Parallelly, it is incident on the interface. But when it reflected at that moment, it will be reflected in this direction, it is reflected in other direction. So when it should happen when the interface is not smooth, then so sometimes one ray will incident and it will be reflected in this direction, another ray incident and it will reflect in the other direction. So the refraction ray, there is no parallel. The both ray are not parallel. Here this both ray, this one and this one will be parallel. Okay, so these refracted rays are parallel, but here it is not parallel. So these are about the specular reflection and the diffuse reflection. So if you have the rough surface, so then the diffusion reflection may happen. If you have the smooth surface, then the specular reflection is there. So the now I come to the this one. So optical fiber. Okay. So optical fiber, normally the optical signal used to propagate. So optical fiber such kind of the fiber which can made up of the glass or plastic or fiber, which is to which helps to direct the. So it is one kind of the optical wavelength. Sorry, waveguide. Optical waveguide. That means it is a one media which guides the optical signal. That's why the name is the waveguide, which guides the optical wave. That's why the name is the waveguide. What is the role of the waveguide? It helps to guide the optic any kind of the wave signal. So it totally depends on the reflection. It depends on the deflection as well as the total internal reflection. If you write the total reflection in the short form, total TIR. Okay, total internal reflection as well as the reflective index. Reflective index. So we know the Snell's law, right? There is one media N1 and 2. This is the perpendicular. This is the interface between two media, and this is the perpendicular line. So if you sorry, light is incident. Okay, so it is refracted. Refracted. it is refracted. Then the angle between perpendicular and the incident angle, this is called the theta 1 and this is called the theta 2. What is the Snell's law? Eta 1 reflexive index multiplication of the reflective index and the sine of the this incident angle. Sine theta 1 is equal to eta 2 into sine theta 2. Okay, eta 1 sin theta 1 is equal to eta 2 sin theta 2. So theta 1 is the angle between the perpendicular and the incident angle, and theta 2 is the angle between perpendicular and the refracted angle. Okay, incident and the refracted. This is the Snell's law. When normally total internal, internal reflection occur. So when the eta 1 greater than eta 2. If the light transmitting from the denser media to rare media, then total internal reflection. Total internal reflection means what? So if it is incident on the interface, no light will be refracted, penetrate through the interface, through the media interface. So it will entirely totally reflected from the interface. So this is called the total internal reflection. To achieving the total internal reflection, some law we have to follow, rule or law we have to follow for achieving the total internal reflection. First one is the reflective index of the light from where the light is incident. That media reflecting index should be greater than the where light falls, that media. So it our medium 1, if light incident from medium 1 to medium 2, so then the reflecting index of medium 1 should be greater than the medium 2. Again, so another law should be followed, that is called the critical angle. So what is the critical angle? This will discuss later. Okay, so here the light incidence from medium 1 to medium 2. So refracted means this is the penetrating in the other side. But total internal reflection means it is not penetrated, it is reflected from the interface. So for occurring this one, total internal reflection, okay. So this ray has to move in this direction, right? This ray has to move in this direction. So this light, this ray is incident in such a way that, so rather transmitting in this direction, if the ray is transmitting parallel to this line interface, parallel to interface, or if theta 2 is 90 degree, then this incident angle is called the theta c. The angle, okay, the incident angle at interface between two media will be the critical angle where the reflected angle is the 90 degree, when the reflected angle is the 90 degree. So rather reflected from the other media, if it is reflecting parallel to the interface, so that is called the reflective ray. Okay, that is the this, if the instead of transmitting in this direction, if the ray is propagating through the parallel of this interface, this line, so if the reflected angle is the 90 degree, then this angle is called the theta c. Theta will be the, suppose theta c, if this theta 1 will be theta c if theta 2 is the 90 degree. This is the critical angle. I hope it is clear. Rather reflected from the other side, if it is reflecting like this, or the theta 2 is 90 degree, then theta 1 will be the theta critical angle. The incident is incident in such a way that it is creating the reflected 90 degree, then it is the critical angle. So when the reflective ray is 90 degree, When refracted ray is 90 degree, then this is the minimum boundary to achieving the total internal reflection. It is the minimum. Once the ray is reached in this direction, then it can create the critical angle. So, total internal reflection. For achieving the total internal reflection, this the theta 2 should be greater than 90 degree. Theta 2 should be greater than 90 degree. Okay, so this is the critical angle for creating the minimum boundary for total internal reflection. Now come to the optical fiber. So optical fiber, this is called the clad. One is the inner layer, this is called the core, another is the clad. Okay, so core reflecting index, suppose eta 1, clad reflecting index in the eta 2. Okay, right? So here suppose it is placed on the in the yard, so eta 2, the outer bound the this the outer is the AR, the reflecting index is the eta 2, which is equal to eta naught is equal to 1. This is the eta 1 and eta 2. So for creating the total internal reflection in optical fiber, because the light has to propagate through the optical fiber, so for the light should follow the total internal reflection. Okay, if light is incident on the core and cladding interface, it should be reflected back. It should not go through the clad layer and the outside. It should be reflected from the interface again. So it will be like that only. Reflect incident on the core media, again it is reflected, and again incident on the core media, again it is reflected. In such a way, it should propagate. So for achieving total internal reflection, first criteria is that eta 1 should be greater than eta 2. Eta 1 should be greater than eta 2. So core medium should be greater than the reflective index should be greater than the clad reflective index. Okay. So first one is the second, the how the light will be incident on the fiber, so that when it reach to the at interface of the core and cladding, it should create the total internal reflection. What will be the minimum angle? What will be the angle for achieving this one? Okay, what will be the minimum incident angle for creating the critical angle at interface of the core? You have to create the critical angle at interface of the core and cladding. To create the critical angle, this is the critical angle at core and cladding interface. That I will discuss now. Okay. So the principle of the fiber optics depends on the total internal reflection, single mode and multi-mode. So this I will discuss later. Okay, the core dimensions radius is like that only 8 to 9 micrometer, 50 micrometer, 60 to 9 micrometer, 100 micrometer. But core cladding radius 125, 125 like that only. Based on the diameter of the core and cladding, some properties will change inside the fiber. So discussion. Okay. So here now come to the acceptance angle. acceptance angle theta naught. What is the acceptance angle? Acceptance angle, minimum accepting angle or minimum incident angle to create the total internal reflection inside the fiber, or to create the critical angle, So how the light is incident at the face of the fiber, that change the, because this is eta naught and this is eta 1 and this is eta 2. So this, due to this, the difference reflective index eta naught and eta 1. Okay, so this the direction of the this refracted ray from that interface between air and the core, that will also change. If this is changed, and again if this falls on the interface of the core and cladding, and this is that how the light will be reflected or refracted, that is also the direction of the ray. That means normally that a term I forgot to tell. So normally reflective index is the C by B, the velocity of light in air and velocity of light in media. So when it hits the interface between two media, the direction will change. Okay, the direction will change from the interface. So that's where the refractive index comes. That depends the ratio of between the two velocity of light in two media. Refractive index, that normally defines the medium of the properties of the medium. If the light falls on the media, how the light will behave, that defines by the reflective index. Okay, so the OA light is incident on the this interface, that will change the effect of total internal reflection at interface of the core and cladding. This is the minimum incident angle for achieving the critical. So suppose light is fall and it is, so it is incident like this way, the light is refracted from that interface, that will not be accepted. Okay, and if light is incident like this way, suppose it hits the interface, again total internal reflection is created. So this is the one ray, this is the one ray, this is the theta naught. So if light is incident like this way, then if after reaching the interface, the reflection ray from this interface, that will hits the that will hits the interface here, that will hits the interface here, and it is reflected through the interface of the boundary. Okay, so the boundary between core and cladding. So that time this is creating the 90 degree, this is creating the 90 degree, this angle is creating 90 degree. Okay, this is the critical angle. So this phi c is called the critical angle. This phi c is here. When the light incident at the core cladding interface, that creates the critical angle. Okay, for achieving the this 90 degree, light should be fall on the core and cladding interface such a way that this angle is creates the 90 degree. That then this incident angle between core and cladding, that is called the critical angle. Corresponding to this critical angle, there will be another angle which incident at the interface of the core and air and core. So that angle is called the acceptance angle. So if ray is incident like this way, and when it comes to here, it will be reflected. Okay, so this is not acceptable. Okay, so when the angle is less than less than the acceptance angle, then it will be acceptable. Okay, then it will be acceptable. If light is incident like this way, then what will happen? Then it will be like that only, it will be like that only, and it will be reflected back. So whatever, so this is the here also, whatever light is incident like this way, so that can create the total internal reflection when those rays are incident at the core and cladding interface. So if it's greater than, if it is less than the acceptance angle, suppose this angle, okay, this will create the reflection ray when it hits the core and cladding interface. So this is called the acceptance angle. This angle should be accepted. If the angle is less than this one, it should not be acceptable. Okay, it should not be acceptable. This is called the acceptance angle. The angle is called when light incident on the interface of the air and core, it should be incident such a way that which can create the critical angle at in core and cladding interface, right? I think this is clear for you, this diagram is clear for you. Okay, so when it is incident like this way, okay, so it may have a chance to reflect it like this way. So I can show you the diagram. You see, so you can see it is greater than theta I. Like this way it is reflecting, it is refracted from the pole. So if it is incident such a way that so it is reflected from when it hits the core and cladding. Okay, so if this incident angle is greater than acceptance angle, then it may have a chance to create the refraction ray when it hits the core and cladding. It should not happen. So when it less than, okay, when it less than the acceptance angle, the incident angle is, so it is like that only. This is suppose theta naught, this is theta I, which is less than theta naught. Then what will happen? It will be hits like this way, which can create the total internal reflection. So our earlier case is this one, greater than theta is greater than theta naught. Then it may have a chance to create the refraction ray. So if the theta is less than theta naught, then it can create the total internal reflection. Okay, again I'm drawing the diagram, so I will show you some the derivation. So there is another term is called the numerical aperture. Numerical aperture or NANA. It is called the sign of acceptance angle. Sign of, so by definition it is defines the light gathering capability. Gathering capability. Light gathering capability. So there will be the value which is in the form of the eta 1 as well as the eta 2. So that this I will derive now. So for that, this is the fiber axis. We have to apply to Snell's law between the AR eta naught and eta 1 against Snell's law between the eta 1 and the eta 2. So by knowing this one, we can derive the equation. Theta naught, this is the theta r, theta c, this is the theta c, this is the theta r, and this is the theta c when this reflected ray is 90 degree. So we'll put this boundary condition and we'll calculate the minimum acceptance angle for creating the for achieving the total internal reflection. This is the theta naught and this is the theta I phi c. So it is suppose phi c is the 90 degree. Okay, so if we apply the Snell's law between AR and the core, then what is the formula? Eta naught is equal eta naught sine theta naught is equal to eta 1. So I think acceptance angle is clear. So the angle for creating the critical angle at core and plane interface, light should be fall in such a way in the in the this axis face of the optical fiber. Okay, that is called the acceptance angle. If it is fall like this way, it cannot create the total internal reflection. When the light is fall like this way, okay, then it can create the critical angle, and if it is fall like this way, then it can create the total internal reflection. So the cone, this cone is called the numerical aperture, light gathering capability. Whatever lights are incident on the fiber, it should be incident such a way that all the light should be create the total internal reflection and propagate in the forward direction. Okay, so now I'm applying the Snell's law at this interface. Eta naught sin theta naught is equal to eta 1 sin theta r. Okay, so here sine theta naught is equal to, sorry, theta r, no, theta naught, I have to calculate the numerical aperture. Okay, sine theta naught is equal to eta 1 eta naught sine theta. Theta, you can see this is one triangle. Okay, this is one triangle. This is phi c, this is theta r, this is 90 degree. What will be the uh, theta r? Okay, theta you can write as a phi c minus 90 degree. Okay, so here I am just putting the theta, not changing anything. Here I will change the value. Okay, another resonance law I am applying at these two interface. Okay, so eta 1 sine phi c is equal to eta naught at critical angle condition, sine 90 degree at critical angle condition. Eta 1 sine theta phi c is equal to eta 2 sine 90. So what is the sine phi c? Phi c is equal to eta 2 by eta 1, sine 90 is 1. So sine phi c again you can write as a 90 minus theta r, 90 minus theta r, eta 2, eta 1. Sine 90 minus theta r is cos theta r, theta 2 minus theta 1. But you have to do the derivation, you have to calculate the sine theta naught. Here in this equation you can see sine theta r is unknown. Okay, so entire sine theta naught should be in the form of the eta 1 and eta 2. So here I am getting the cos theta is n2 by n1. I have to calculate the sine theta. So there is one trigonometric formula. It is what it is, sine square theta plus sine square theta cos square theta is equal to 1. So what will be the sine theta? Theta will be root under 1 minus cos square theta r. Okay, cos square theta. So what will be the sine theta now? Sine theta is equal to root under 1 minus n2 square by n1 square. Because instead of cos square theta, I am putting n2 square by n1 square sine theta. So this the value of the sine theta, this I will put here only in this equation. In this equation I will put the value of sine theta. Okay. So here I am writing what will it will be. It is the sine theta naught is equal to that, this one is eta 1 eta naught root under 1 minus eta 2 square and eta 1 square. If eta naught is 1, eta naught is 1 for air, so sine theta naught will be, if you do some manipulation, then what it will be, it will be like that only, eta 1 square minus eta 2 square. Okay, so here I am putting eta naught is equal to 1. If you do some manipulation, it is that. So that value is the numerical aperture. So where it is the definition, numerical aperture determines the light gathering capability of fiber. Amount of the light that can be excited by the fiber, it calculates the numerical aperture. Okay, so normally numerical aperture value is 0.13 to 0.15, right? So I think the derivation is clear. Just I have applied some new mathematics and I can calculate the numerical average in terms of the refractive index. The derivation already I have discussed. So that if the total internal reflection happen on the optical fiber, so it will be like that only. The phi is the alpha is the acceptance angle and theta c is the here critical angle. So like if light is incident like this, it should create the total internal reflection like this way in the optical fiber. Okay. So that means the eta 1 should be greater than eta 2, and it when the light is acceptance on the fiber, incident on the fiber, it should create the theta c or critical angle when it hits the coherent cladding interface. If it follows, it will not follow this one, then they cannot create the total internal reflection. So there is one numerical. So here the eta 1 and eta 2 are given, and the light is operating in 820 nanometer. So what will be the numerical aperture? Numerical aperture is root under n1 square minus n2 square. This is this one, 0.153. Okay, so calculate this and you will get the 0.943, and acceptance angle is the NA is equal to sine theta A. So if we put the 0.53, so what will be the theta A? Theta will be the sine inverse 0.153. You will get the 8.8 degree. This is the acceptance angle. This numerical, what is the question? The optical fiber, the reflective index, that means co-reflective index is the 1.5. So if what will be the clad reflective index? So to ensure the total internal reflection when it hits the coherent cladding interface, then what will be the eta 2? So if the light is traveling and creates the 5 degree of the fiber axis, when light is incident, it is creating the 5 degree of the fiber axis. That means the theta r. Okay, not this incident acceptance angle is the theta r. It is creating the 5 degree with the fiber axis. That means the reflected angle when it hits the interface of the coherent cladding. Okay, this is the theta r. Theta is 5 degree. Then you have to calculate the cladding interface. So if you put the Snell's law, so in the coherent cladding, the n1 sine phi c is equal to n2 sine 90 degree. Okay, see, you know the value of n1 and you have to calculate the n2, but you have, before calculate the n2 you have to know about the phi c. Okay, phi c is this one, right? This one is the phi c. You know this one. Okay, so by putting the trigonometric formula, if you know this one, you want to calculate the phi c, you can get, because the phi c is equal to, that will, from the derivation also you know, 90 degree minus theta r. Okay, so what will be the phi c? Phi c is equal to 85 degree. As the light incident and it's creating the 5 degree of the fiber axis, that means you have to understand that this is the theta. So if you know the theta, you can calculate the phi c, 85 degree. Now if you put under the n1 sine 85 degree and 2 sine 90, then you can calculate the eta 2, reflecting index 1.494. That means if the reflecting index 1.494, then if his light is incident at a 5 degree the optical fiber, it can create the total internal reflection. Again, if you know the eta 1, eta 2, you can also calculate this angle. Also, opposite thing also you can uh, estimate, right? So these are about the how the light can fall on the optical fiber for achieving the total internal reflection. What are the critical angle, acceptance angle, and the numerical aperture? And I have shown how can you calculate the numerical aperture if you know the reflecting index and reflective index too, or if you have the value of the incident angle or reflected angle, how can you calculate the reflective index? This I have discussed in the today's lecture. And the next class I will start with the modes and what are kinds of the modes are there, single mode, multi mode, and what do you mean by the modes. This I will discuss on the next class. Thank you.